It's National Corduroy Day. Or, no, that's the 11th, sorry.
I was gonna say, I don't have a corduroy.
It's the date that looks most like corduroy.
What? Oh, it is.
Like 11/11.
It's ridiculous.
I think that's like almost near that.
He was like,
So today I'd like to start a new topic, which is stomata. I don't understand. So stomata are turgor operated valves. Right? They're actual holes in the surface of the plant. And the hole is surrounded by two cells, each of which is called the guards. The Greek word stoma means mouth. I guess that's a good name. When the guard cells are turgid, when their pressure potential is high, the stomata are open. And when they're flaccid, if their pressure potential is low, the stomata are closed. And when they're closed, they're really closed. Like, nothing can get through them. They present a really high resistance to the movement of water vapor out or CO2 in. But for the plant, it has opposing priorities. On the one hand, it wants to open the stomata as wide as possible so that it's easy for CO2 to get in, so it can be fixed by photosynthesis and the plant can increase its biomass. But on the other hand, when the stomata are open, it's losing water. And so it doesn't, usually they don't want to, plants, oftentimes plants have difficulty if they lose too much water. So it's, on the one hand, open them as far as possible, but on the other hand, keep them closed so you don't lose a lot of water. They're opposing priorities, and the plant has to balance this set of opposing priorities in the face of changing environmental conditions. And so a good reference that builds on this idea is Ian Cowan's chapter in the physiological plant ecology volume of the Encyclopedia of Plant Physiology back in 1982. And he doesn't shy away from the use of math in his analysis of these opposing priorities that plants have. But it's a good reference that delves into this area in some detail. All right, so let's consider stomata. This table is from Fitter and Hayes' book called Environmental Physiology of Plants, and it lists some characteristics of stomata. So here's the plant species, and for example, Zea mays. The frequencies of stomata on the upper and lower surface of the leaf, on the abaxial and adaxial and abaxial surface of the leaf. In maize, 98 stomata per square millimeter on the upper surface, about equal number, 108 on the lower surface of maize. Per square millimeter, right? A square millimeter is pretty small. And it's got 100 stomata in that little space. So the stomata are small. Here are the dimensions, typical dimensions in microns. 100, what is that? I can't read. 38, I think it says, by 1943. You see this and the length of the stomatal pore when it's open. When the stomata are open in maize, that area represents 0.7% of the total leaf area, consists of an open space. That's a pretty small area. But stomata are that, because of the arrangement of the stomata, it's very efficient at moving gases to or from the leaf surface. if you compare the transpiration rate of a leaf with open stomata, even though the pore area is small, what's the highest one here? 2%, less than 2% of the total area. It can still transpire up to about 50% of the amount of an open water surface of that area. So just because it has a small open area, it's very efficient at moving water vapor away. And the reason for this is for an open water surface, the diffusion away from that surface is pretty much one-dimensional. But for stomata, for a leaf with open stomata, the water vapor can diffuse away in 3 dimensions. I could only draw 2 of them here, but you get the idea. You know, from each hole, you have diffusion in 3 dimensions away from that opening, not in 1 dimension like an open water surface. So this arrangement is very efficient. It won't move quite as much water as open surface, but it's very efficient considering how small an area is actually open in that leaf surface. So you can see for different species, different characteristics for stomata. Notice that some of them, this is a fern, Pteridium aquilinum, no stomata on the upper surface. Carpinus betulus, that's a woody, what's that? Carpinus betulus. Who knows the name of that? Carpinus. I used to know these names. Anyway, it's a woody plant. Here's Quercus robur is English oak, Tilia europa, that's what they call lime tree in England, but we call basswood or linden. No stomata on the upper surface. Plants that have no stomata on the upper surface are called hypostomatas. Plants that have stomata on both surfaces are amphistomatas. Right? And hypo means beneath, so typically if the stomata are only on one surface, that's the bottom surface, the abaxial surface of the leaf. And that's really common in woody plants, to have the stomata just on the bottom surface of the leaf. All right, so here's just some examples. Here's maize with about equal frequency of stomata on the upper and lower surface. Here's cocklebur, again, about equal numbers of stomata on the upper and lower surface. Notice that cocklebur has even more stomata per square millimeter than maize. What's the winner here? Well, here, this one, this linden, 370 stomata per square millimeter. That's a lot of folds in the leaf. But each one's really small. Okay, here are examples of amphistomatous leaves with unequal numbers of stomata on both surfaces. Here's spiderwort Tradescantia. This is the one that Shackle used in that experiment where he was comparing the thermocouple psychrometer and other ways for measuring water potentials. He used this plant. And here's tobacco. Unequal numbers of stomata on each surface, but they're amphistomatas because they have stomata on each surface. Hypostomatus species, here's that fern that was listed, and Quercus robur, the English oak, is here too. And as I say, lots of woody plants are hypostomatous. What about a pine? Cross section of, what is this, Scots pine? Cross section of this pine needle is this. What's the upper and what's the lower surface of something like that? Good response. I don't know. And it's so twisted too. Okay, so several years ago, we worked on a project in Saskatchewan in Canada, and And one of the things we had to do was estimate the leaf area index of pine trees and spruce trees. Well, you know leaf area index, right? Leaf area index of maize, right? That's easy. What is it? It's the leaf area per unit ground area. Right? Actually, it's half of the entire leaf area per unit of ground area. Because two surfaces, you know, if you consider each surface, it's half the leaf area per unit ground area. So one of the things that had to be done in this project in Canada, how are you going to define the leaf area for a pine tree or for a spruce? You know, some spruces have needles cross section of which is like this. Some pines are like Scotch pine like this, some pines like this. You know, they vary all over the place. How do you get the leaf area for something like that? Well, not how do you get, how do you define the leaf area? Well, it's defined the same way. Well, for consistency, it's good to define it the same way as you do for any other plant. And that is half of the entire surface area per unit ground area. Right? That's consistent with other ways of doing leaf area index. Then the question is, how do you measure the surface area of something like that? You know, you put it on, you do what you do with other plants, right? You have a leaf area meter. Have you used those things like the conveyor belt thing and put the leaf through and it tells you, it counts up the leaf area. If you put something like this on there, what you get is the projected leaf area. Same for a flat leaf. You get the projected leaf area, which is this surface. That's underestimating the leaf area for this kind of a thing. So projected leaf area isn't quite right. How do you measure leaf area? There's ways to do it. There's ways to do it. Anyway, something to think about. It's not so easy. Tedious is the word that comes to mind. Anyway, for Scotch pine, there are about equal frequency of stomata on this surface as there are on this surface. And in general, that's true for pines. You know, if you have this arrangement, you'll have about equal frequencies of stomata on each of these surfaces. That'll be important when we quantify stomatal conductance of stomatal. Yeah. In guard cells, okay, so plants, as I keep saying, plants have no way to regulate their pressure potential. They can't change their pressure potential directly. And so how can they open and close these Turger-operated valves if they have no control over the pressure potential? They change their osmotic potential. So guard cells, compared to all other cells in the plant, guard cells are characterized by their enhanced ability to osmoregulate. They can change their osmotic potential quickly in response to changing conditions. And by changing their osmotic potential, okay, so let's consider stoma that's closed. The guard cells are flaccid. The pressure potential is low, close to zero in those cells. Now, the plant gets a signal to open the stomata, something, and believe me, we'll go into these signals in detail. The most important probably of which is light. Okay, so you have a plant in the dark, its stomata are closed, and you turn the lights on. What happens? The guard cells accumulate solutes. That causes a disequilibrium between their total water potential and the water potential of the cells all around them. By increasing their concentration of solutes, decreasing their osmotic potential, causes water to move from the surrounding areas into those cells, increases their pressure potential. That increasing volume increases their pressure potential. Remember this Hefler diagram. Increasing volume increases the pressure potential, and the stoma opens. The guard cells deform in such a way that a hole opens up between them. And that deformation is caused by uneven mechanical characteristics of the cell wall in the guard cell. So very thick portion here, relatively thinner portions here, so that when the volume changes, this part stays the same, but this part gets bigger and it deforms in such a way that a hole opens up between those two cells. Right? That raises a bunch of questions that I'll try to go into in some detail in the next couple of days, next couple of classes. All right. So, one thing that we have to know is, how do you know how open the stomata are? How can we quantify the stomatal conductance, or conversely, stomatal resistance? Okay. Stomatal conductance is the idea of how open the stomata are in a given situation. And the units that are used for it used to be velocity units, used to be centimeters per second or meters per second for stomatal conductances. And those units are still used in some areas, like micrometeorology. People tend to use velocity units. But the physiology people, being concerned with chemical reactions and the molecules and things, tend to use molar units. So most stomatal conductances now for physiology are recorded in terms of moles per meter squared per second. And it's in terms of what you're talking about. So for transpiration, we're talking about water vapor leaving the leaf. And so appropriate unit would be moles of water vapor per meter squared of leaf area per second. Shortened to moles per meter squared per second, as you can see in this graph right here. So here's stomatal conductance in moles of water vapor per meter squared of leaf area per second. Here's light intensity, micromoles per meter squared per second. And you can see when it's dark, the stomata tend to be closed. And when it's light, they open up. A high value of stomatal conductance in molar units may be a value of 1 mole per square meter per second. Low value, 0. And so for this tree, represented by this graph, these are fairly low stomatal conductances. The maximum conductance here is less than 0.1 mole per square meter per second. And you can convert to velocity units if you know the pressure and the temperature and something like that. All right. Small stomatal conductances are not unusual for coniferous species like this Chilean cedar. Right? Now, it gets a little more complicated, or it is a little more complicated, because how can we deconvolve that, or the stomatal conductance is only one of a series of conductance, of a group of conductances that we have to consider when talking about the total leaf conductance for water vapor, let's say. Because the stomata is, the stomatal pathway is only one way that water can leave the leaf. Water can move right through the cuticle. So there's a cuticular conductance associated with the leaf. And on any surface, there's a layer of still air right next to it. And that's called the boundary layer. And that represents an impediment to the diffusion of water vapor out or CO2 in. That's called the boundary layer conductance. So we've got the stomatal conductance, the boundary layer conductance, the cuticular conductance. What's more, we've got that combination on one surface and the parallel combination of that on the other surface for amphistomatous leaves. And so it can involve a bit of algebra to separate these conductances into their component conductances. And a lot of times we're interested in what the stomatal conductance is, because that's what the plant has control of. It's got less control over the boundary layer conductance and the cuticular conductance. Luckily, the cuticular conductance is usually very small compared to the stomatal conductance and the boundary layer conductance. It's a very small value, at least an order of magnitude smaller than the other conductances, so oftentimes that's ignored. The cuticular conductance is ignored. But the boundary layer conductance, this impediment due to the layer of still air next to the leaf, is an appreciable factor and can't be ignored. So if we're interested in measuring the stomatal conductance, how do we do it? One way to do it is to put the leaf in a chamber, in a gas exchange cuvette in a small chamber, and measure the water vapor concentration going into the chamber and the water vapor concentration leaving the chamber. If the stomata are open, the air will have more water vapor when it leaves the chamber than when it enters the chamber. And by using the appropriate equations, you can estimate the total leaf conductance for water vapor in such a situation. That's the total conductance. What's the stomatal conductance? Well, for that, you have to know something about the boundary layer conductance and then deconvolve those component conductances from the total leaf conductance. Okay. Let's consider a hypostomatous leaf, right? So here we have stomata on one surface. These are the four examples. Okay, so there is a stomatal conductance on this surface, and there's a boundary layer conductance on this surface. The total leaf conductance is the series combination of these conductances. Do you remember how to add conductances in series? So the total conductance for this situation is to add conductances in series, you use this formula. Right? So this implies that all right, here we go. If we do the boundary layer conductance here and the stomatal conductance here, right, for multiplying both of these by 1, so it doesn't change anything, but then we can put them on the same basis. Right? And this implies then that the leaf conductance is given by this formula. Okay, so we need to know the boundary layer conductance. If we have a measure of the total leaf conductance, like in the gas exchange cuvette, we need to know something about the boundary layer conductance in order to tease out the stomatal conductance. This is for hypostomatous leaf. For amphistomatous leaf, now you've got conductances in series. I mean, in parallel from the top and the bottom. And to come up with the parallel combination of conductances, you just add them. So the total leaf conductance for amphistomatous leaf is, and let's assume, just to make things simple, that the stomatal conductance and the boundary layer conductance are equal on the top and the bottom surface of the leaf. Then in this case, just add them. So adding conductances in parallel, you just add them. Just like resistances in series, you add them. But for conductances, it's the opposite. Anyway, don't worry about that kind of stuff, because we won't be making these kinds of measurements and expecting to figure them out. I mean, it raises a good question though, something worth thinking about at least, and that is, if you have a gas exchange cuvette and measure the transpiration rate from a leaf. Okay. You know what? Are you familiar with leaf gas exchange? Like with the Lycor 6400, 6800, a way of measuring photosynthesis and stomatal conductance for a leaf. You put the leaf or a piece of the leaf in a small chamber, and you measure the CO2 concentration going in and the water vapor concentration going in, and here's your leaf in the chamber. And then you measure the CO2 concentration going out and the water vapor concentration going out. And for example, the transpiration rate is this difference in water vapor divided by the total pressure times the total leaf conductance for water vapor. So total conductance, like we've been saying, is this parallel combination of the two surfaces, parallel combination of the series combination of the boundary layer and small conductance on each surface. So making a measurement in the gas exchange cuvette, we can measure this, we can measure this, we can measure this. We get an estimate of the total leaf conductance. So we need to know something about the boundary layer conductance to say what the stomatal conductance is. And the way that, at least for the Lycor system, the way that's recommended is to use a piece of damp, a piece of wet but not dripping filter paper, a replica of the leaf that's made of filter paper, because that has the stomatal conductance. There is no, it's infinite stomatal conductance. There's no impediment caused by stomata. It's all boundary layer. So if you determine the total conductance of a piece of wet filter paper in the cuvette, that's the boundary layer. That represents the boundary layer. Anyway, and similar for CO2 concentration. Okay, as I say, cuticular conductance, we can ignore. Stomatal conductance depends on a lot of factors, light, EPD, abscisic acid, we'll get into all that. Boundary layer is affected by the size of the leaf, and in particular, the wind speed that's blowing over the leaf surface. It's also affected by any surface roughness, like presence of hairs, trichomes, whether or not the stomata are sunken beneath the surface of the leaf, or whether they're right in the plane of the leaf like this. And things like that. Okay, well, this just shows, this is from Monteith's book, Principles of Environmental Physics, and it shows resistances here, but you get the idea of this parallel pathway of the resistances or conductances. And I don't know if you're familiar with electrical schematics, but this arrow through the resistor means it's a variable resistor. This is a fixed resistor. So the stomata have a variable resistance. The boundary layer is variable because the wind speed changes. Okay. Let's look at the cuticle for a minute. And these pictures are taken from a dead website, a dead link. You can't find it if you go there anymore. But if we go, how do I do it? Try this. Use DuckDuckGo. You know that search engine? So, unlike Google, DuckDuckGo doesn't remember what to search for. So lots of people like it. Anyway, if you search for epicuticular wax, and then just look at these images, you get all kinds of images. So look at these. Look at some of these pictures. This one. Look at these waxes on the surface of these. Really weird. So intricate. You know? Here you can see the stomata. See, and then wax the surface. Anyway, so you can find things that way. Anyway, here are the epicuticular waxes on a rose. You can see the stomata here, and then the rose, lily of the valley. Here's Strelitzia, the bird of paradise. Here's Equisetum with these funny dots. A tree fern, and see others. They're really varied and quite elaborate, a lot of cases. And sometimes the nature of these are used for classification of different species.